Welcome to the deep dive. Today we're jumping into generative AI, really exploring the core ideas behind how systems can actually create completely new data. Here's where it gets really interesting.
Yeah, what's fascinating here is how these generative models go beyond just, finding patterns. They learn the rules well enough to generate entirely new things. We've seen some huge impacts already, especially with images and audio generation. It's quite mind-blowing.
Definitely. And just to kick things off, let's try something. Look at these three faces I'm showing you. A, B, C. Which one do you reckon is a real person? Take a sec. Got your guess. Okay, well, the answer is none of them. All three are completely fake.
Exactly, and that right there just shows the power, the realism we're talking about with generative modeling.
It really does.
And it's a big shift, from traditional supervised learning data with labels to unsupervised learning. Here, we often just have the raw data. The model has to figure out the underlying structure, the probability distribution. Once it learns that distribution, it can then draw samples from it, create new stuff that looks like the real data. If you connect this to the bigger picture, well, it's about AI learning to understand and recreate parts of our reality.
So, okay, you can make new data. Why should we care? I mean, beyond cool fake faces, what are the big applications here?
Oh, it's incredibly valuable. Generative models let us uncover sort of hidden features in data that can help us build fairer data sets, for instance, find biases. They're also great for outlier detection. Think about self-driving cars needing to handle really rare situations. And of course, the most obvious one, just creating new data samples. That's the engine behind a lot of what we see in natural language, computer vision, even healthcare now.
Right. And a really key idea in a lot of these models is something called latent variables.
Yeah, think of Plato's allegory of the cave. You've got prisoners seeing shadows on the wall, right?
Mm-hmm. The shadows are like the data we see.
Exactly, the observed data instances. But the real objects casting those shadows, those are like the hidden underlying latent variables, the core features that actually define what we're seeing. The goal is to capture those hidden features, learn what makes the objects or the data tick.
Okay, let's unpack this a bit. Autoencoders. You mentioned them as being pretty intuitive. How do they work, let's say, with handwritten digits?
Sure. So an autoencoder takes that input digit and it first encodes it, squeezes it down into a much lower dimensional space called the latent space. That's the encoder part. Then a decoder part tries to reconstruct the original digit just from that compressed latent representation.
So it's compressing and then uncompressing.
Essentially, yes. The whole point is to force the model to learn the most important distilled features in that latent space. It's a form of data compression, really, and it's trained unsupervised. We use something called reconstruction loss, basically measuring how different the output is from the input, maybe mean squared error for images. It learns to minimize that difference without needing any labels for those latent features.
Okay, that makes sense. Then we get to variational autoencoders, VAEs. They add randomness, stochasticity. What's that about?
Right, that's the key step up. Instead of mapping an input to a single point in latent space, a VAE maps it to a probability distribution, usually described by a mean and a standard deviation. This adds a bit of controlled fuzziness.
And how does that change how they're trained?
Well, the loss function gets two parts. You still have the reconstruction loss, like the basic autoencoder trying to make the output look like the input. But you also add a regularization term, often KL divergence. This term basically encourages learned distributions in the latent space to resemble a chosen prior distribution, like a simple normal distribution, a bell curve.
And why do we want that? You mentioned properties like continuity and completeness for the latent space.
Exactly. Continuity means similar inputs should map to nearby points or distributions in the latent space, no sudden jumps. Completeness means if you pick any point in that latent space and decode it, you should get something sensible back, not just garbage. The regularization, pushing towards that smooth normal distribution, helps enforce both of those properties, makes the space well-behaved for generating new things.
Okay, so it makes the latent space structured.
Precisely. And there's a clever bit of math called the reparameterization trick that lets us actually train these things properly with backpropagation. Even with the randomness involved, it separates the randomness out.
And VAEs are known for being interpretable.
Mhm.
Right, you can actually see what those latent variables learned.
Yes, that's a major strength. You can often tweak values in the latent space and see meaningful changes in the output. Like, one latent variable might control smile intensity, another head rotation in generated faces. It helps us understand what the model learned, which is super important for trust and debugging.
Okay, moving on. The other big foundational class, generative adversarial networks, GANs. How are they different?
So while VAEs are great for understanding the data structure and those latent variables, GANs are often laser focused on generating the most realistic samples possible. They work by transforming simple random noise into something that looks like complex, real data.
And this is the one with the two networks fighting each other, the generator and the discriminator. Sounds kind of fun.
It is a really clever setup. You have the generator, whose job is to create fake data starting from random noise. And you have the discriminator, whose job is to look at a piece of data and decide if it's real from the actual data set
Yeah.
or fake from the generator.
Like a detective.
Exactly. It's this constant game. The generator tries harder and harder to fool the discriminator. The discriminator gets better and better at spotting fakes. This forces the generator to produce incredibly realistic outputs. If you imagine points on a line, the fake data points get pushed closer and closer to the real ones until the discriminator just can't tell them apart anymore.
So the end goal is perfect fakes.
Ideally, yes. The generator learns to mimic the true data distribution perfectly. Now, training them well, that can be tricky. Avoiding things like mode collapse, where the generator only makes one kind of fake, that's a whole other challenge.
But like VAEs, you can also play around in the input space.
Right.
Interpolate the noise.
Absolutely. Smoothly changing the input random noise to a trained GAN often leads to really smooth, interpretable changes in the generated output. Changing hair color, adding glasses, that kind of thing.
And there are variations too. You mentioned cycle GANs.
Right. Cycle GANs are fascinating. They do unpaired style transfer. So you can teach them to turn horses into zebras or maybe summer scenes into winter scenes without needing exact before and after pairs of images. Or even in audio, maybe changing one person's voice to another's by working with spectrograms, those visual maps of sound.
Okay, so let's quickly recap. VAEs and GANs, the two big foundational models.
Fundamentally, yeah. VAEs are strong on density estimation, learning that interpretable latent space, giving us insight.
While GANs really shine at generating super high-quality, realistic samples using that adversarial training approach.
Exactly. And look, these two approaches, they really laid the groundwork for almost everything exciting happening now. Diffusion models, the huge language model, a lot of the core ideas trace back here. They showed us how to build AI that isn't just analytical, but can be genuinely creative.
So wrapping up, considering the incredible realism we've seen and the interpretability offered by things like latent variables, here's something to think about. How could really understanding these underlying features help us build AI systems that are not only powerful, but also more responsible, maybe fairer, less biased in the future? Definitely something to mull over. Join us next time for another deep dive.